Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over another application of definite integration. It's in fact finding the volume of a solid. And this time we're going to use the shell method to write and evaluate the definite integral that represents the volume of the solid generated by the plane region, which I'm going to say a few words about in a few seconds, okay? And we're going to revolve this region about the x-axis. So let's see what the region looks like. That's y equals 4x squared. That's a parabola. And we have the y equals 4 horizontal line and x equals 0, which is the other name of y-axis, vertical line. So let's see what the region looks like quickly. Okay, so as you see that within the region, on the right-hand side, we have the blue curve. At the top, we have the purple line. And on the other side, as you see, we have the y-axis, making up our green region, and we're going to revolve this region about x-axis. Okay, and we're using the shell method. That means I'm going to take slices within the region parallel to the axis of revolution. So so that means my slices are going to be horizontal. So that means the thickness is going to be determined by dy. So everything is going to be written in terms of dy. But before we get started, let me just remind you what the shell method is when the axis of revolution is horizontal. All right, so this is the big picture. So we have the volume of a solid of revolution by the shell method. And depending on which axis you go with for the revolution, you get two different formulas. And we're particularly interested in the very first column and the very first picture on the left, because we have the axis of revolution to be x-axis, which is horizontal. And as you see at the left corner, we get a slice of a rectangle parallel to the axis of revolution. Let me just make this bigger. Okay, so so yeah. Then once you revolve that rectangle around the x-axis, you're going to get a shell. And you need to have the radius and the height of the shell written in terms of y. So these are p and h respectively. So then you're going to find the volume of that representative shell as 2 pi times the radius, which is p of y. That's the circumference of the circle, times the height of the shell, which is 2 pi times p of y times h of y. That's the surface area of the shell. But if you multiply that by the thickness, then you get the volume of the representative shell. Okay, so let's go back to the formula. So the formula goes like this. Since the integral is about dy, so we're going to find the y range in the light blue region on the left corner. So y's are ranging in between c and d. So we go ahead and write the volume integral as like 2 pi integral from c to d, p of y, h of y, and dy. All right, so let's see in our case, what kind of like volume integral will pop in our case, and we're going to determine all the pH and C and D accordingly, and we're going to evaluate the final integral obtained or representing the volume of that three-dimensional object I showed you in the beginning. All right, let's get started. All right, let's take care of this problem. We're going to use the shell method to write and evaluate the definite integral representing the volume of the solid generated by revolving the plane region, obviously bounded by y equals 4x squared, y equals 4, and x equals 0, which is the other name of the y-axis. And y equals 4 is a horizontal line, and this is a parabola. So why don't you go ahead and plot this y equals 4x squared and y equals 4 in the same plot. And they will intersect at some point. Let's just quickly find where they intersect. So let's just set the y values equal. Okay, so that makes it x squared equals 1 and x equals plus minus 1. Okay, so at x equals negative 1 and at x equals 1 they intersect, but we are sort of like our region is bounded by the y-axis and y equals 4. So I think we only get, let me just write this back, but we only get plus 1, okay? Because again, on the left, the region is bounded by the y-axis, so you don't get to see x equals negative 1. All right, so why don't you go ahead and plot this region maybe from 0 to 2, just or 0 to maybe, yeah, 0 to 2, just to see where the region is, and you can actually zoom in or play with your x min, x max values. Here is what my outlook looks like. I got y equals 4 minus y equals 4x squared. That's the blue curve. Okay, so this is y equals 4x squared, and the purple one, which is the horizontal line. I sort of like got a wider view of that because we're gonna need to see what the region looks like. And as you see in the bottom, the region is bounded by the blue curve. On the top, it's the horizontal line, and on the left, it's the y-axis. Okay. So here, what is asked in the question is to come up with the volume generated by revolving this green region around about the x-axis. Okay, so let me just show you what kind of like three-dimensional object we're talking about. So again, this region is going to be revolved around x-axis. Let's see what we get. So we start right here, and then we start revolving it. All right. All right, something like this. So as you see that you have like a horn-shaped inner part of that volume, but it's like cylinder, and you take out a horn-shaped three-dimensional part of that, and then you have the leftover volume. So the question is to find, the question is like, how do you find the volume of this three-dimensional object, okay? And we were specifically told to use the shell method, okay? We were specifically told to use the shell method, and in the shell method, we always get slices parallel to the axis of revolution, okay? Parallel to the axis of revolution. So what does that mean? I'm just going to get a horizontal slice, okay? So I'm just screw this here. Okay. Here we go. This is my this is now my representative slice, okay? And I'm going to revolve this around, okay? So you see, and let's say like since the thickness part is on the y-axis, so in other words, the thickness is going to be dy in that regard. And I'm going to get a shell like this. And to be able to write down the volume of the shell, let's go back to the formula here. Here we go. We're doing the axis of revolution to be like x-axis. So here we go. We're in this case, in the very first case, okay. And all you need to have is the height, and the radius of the shell, okay. So all I'm trying to say is this, okay. So after the revolution here, right, you have, let's just get a better one. Here we go. You need the h of y and the radius of the shell. Once you have it, once you have in fact both of them, you're going to write the volume as 2 pi times the radius, so it's the circumference of the bottom, times the height of the cylinder, and times the thickness. Okay, so this is the formula that we're about to use. Now let's see how the radius and height, in our case, are determined. Okay. All right. First off, let's start with the fact that, let's say like this slice is y units far from the x-axis, and remember that we're going to write everything, meaning radius and height, in terms of y variable. Okay. All right. So then I'm going to find the height. Height is just right here. So and if you consider the very right end of the slice here, the coordinates of that are x and y, obviously, but x is determined by the curve. So I'm going to rewrite this curve as x equals y over 4 radical. Okay, so that the x coordinate, when y is y, the x coordinate written in terms of y would be x equals here radical y over 2 if you simplify that. Okay, so this would be the h of y I'm after. Let me just write cleaner. H of y, and then this is the p of y. Okay. All right, we can go ahead and write down the volume of the representative shell. So that's going to be 2 pi times the radius, which is p of y, times the height, times dy, the thickness. Okay, so 2 pi, p is y, and this is radical y over 2 times dy. Okay, so now since we're going to write the integral in terms of y, I need to know the y limits of the region. So here we go. So y limits are determined by the lower limit is touching the origin. So here we go. And then the upper limit is determined by the horizontal line. So y's are ranging in between 0 and 4. Okay. So let's go ahead and finalize this by writing the integral corresponding to this integral, corresponding to this volume, integral from 0 to 4. Okay, so y times radical y over 2 times dy, right? Let's simplify this. Radical y is y to the power of 1/2, and y times radical y is going to be y to the power of 3/2, and I'm going to pull the 2 out, the bottom 2 out, so it's 2 pi over 2, that makes it just 1 pi, right? And then this is dy. Okay. And we can integrate this in one shot. So y to the power of 5/2 divided by 5/2, and you have pi here, and you have 0 to 4. Okay. And that's in fact equal to 2 pi over 5, y to the 5/2 from 0 to 4. Well, let's use the fundamental theorem of calculus. So let's plug in 4 for y. 2 pi over 5, 4 to the 5/2. And if you plug in 0, it's going to be all 0. Okay. All right, so 4 to the power of 5/2 is 2 to the power of 5. Okay, so that's 3264 pi over 5. Okay. So we can go ahead and write that the volume here is 64 pi divided by 5. Okay. Again, we were specifically told to use the shell method to come up with the volume here, and to be able to use the shell method, you need the radius of the bottom of the representative shell and the height of the shell. Okay. And the shells are always selected based on the fact that they should be parallel to the axis of the revolution, so that when you revolve that, you get a shell type 3-dimensional